Thank you for the introductions. And before proceeding to my talk dedicated to Terahertz imaging, I'd like to thank organizers for inviting me. It's a big privilege to collaborate with people from Warsaw. We have long-term relationships and cooperation topics. And since it's the last lecture in this nice series, and dedicated to imaging, I will try to touch briefly what was given before, not going to the details, but mainly touch several topics which in the different angle, like application in imaging, and in particular devices which are developed earlier in a very specific way with containing elegant physics. But here try to touch from the angle of parameters exactly focused for imaging, and the main trend and main focus will be how we can use these devices to construct compact system, which usually not big, not in a meter scale, but only centimeter scale, and should be acceptable for real-time, for real and implementation and good quality recordings. So imaging and towards compact and effective systems, and my contents of my talk will be just intro. First, we'll talk about the principles of terahertz imaging and how it appeared, and what the properties of terahertz can be used for this approach. And today, main focus will be spectroscopic imaging, how we can extract spectroscopic information from the image when we do not directly recording the spectrum itself. We'll talk about compact emitters and detectors, and how we can go with flat optic solutions. These three components, emitters, detectors, and flat optics, is a main in order to reduce the size of the system and making them friendly users. And then we'll talk about mainly the second part. Will go how we try to engineer terahertz light using silicon diffractive optics, and also we're going to the relatively novel topic on application of terahertz structured lights in terahertz imaging, and finally I would underline non-paraxial terahertz imaging, in particular when we want to implement imaging or imaging system directly on a chip. It means dimensions of the optical systems, it's very compact. Focus becomes very short in that optics changes. And this is in particular important to understand how the principles can be applied for that. And finally, outro, what we could expect tomorrow. So what was done yesterday, what we have today, and what we expect tomorrow. And so, but I start from very general statement, what in fact the place of terahertz in electromagnetic scale is a little bit specifics, probably not only important for not in design of devices, because it's a bridge between electronic and photonics. It means that we have no clear rules how we can connect both worlds in a one device, because in a terahertz photon, let's say if 1 terahertz photon is only 4.1 MeV, it's and if we compare it with room temperature, it's 25 MeV. It means room temperature operation. It's not so convenient for terahertz range. It means that this way, it means from photonic sides, we can combine so-called electronic approach in terahertz. It means applying lasers, femtosecond-based lasers to generate them and detect them as well. But if we want to make a compact system, femtoseconds lasers hardly can be applied, because usually lasers needs to be placed on optical tables. It's usually 1 meter width and 2 meters long, and we have still a lot of optical component. It means systems becomes relatively bulky. It means if we want to go to a very small system, effective system, and friendly user systems, in operating in real implementation conditions, solid state approach could be good. And it means we'll talk about how we can do terahertz solid state-based devices and apply them for terahertz imaging. That is, terahertz are very specific wavelengths 10,000 times higher than mobile phone operates, but had a property to propagate nearly without losses in the electric stuff. It means paper, cartoon, post packages are very good for terahertz light because absorptions were weak. But in that case, we can see inside these packages, making testing of materials and to see, let's say, apply them for security without opening the stuff and to see contents of the packages. So seminal work, I would start from the principles. Seminal work is Martinas, Bihu and Martinas in Bell Labs nearly 30 years ago, and they showed very nice picture of chip, semiconductor chip, and the main stuff was to see that we have a not chip exactly, but his connection inside this plastic frame. That was advantage because in indicating that terahertz can be very good non-destructive instruments to do this. So, but if we look at the principles of imaging in the setup, so their setup was relatively big one, and they have a femtosecond laser, and the sample was placed between the optical lenses. So we were scanning delay line and huge interesting mechanics, a lot of recording stuff. But system was bulky, but in fact it allowed to record this very nice stuff. So in case how it works, I mean it's how to imagine and how we can show it. Illustration of this principle. It means it's like principle of so-called time domain spectroscopy. When you have a let's say slightly different stuff, we have a terahertz emitter and terahertz detector here, but in fact femtosecond lasers, the beam was split into arms, and here we're using delay line, which allows to record so-called transient in a terahertz detector. So if we're running the movie now, we'll see the transients of shape here, and we see that it looks like this, but in fact it's not real terahertz. It's Fourier transform of the transient shows us the spectrum. And if you look at the scale, I mean, we have a transient, here is delay time, and here it says transient. It's classical picture, and the main advantage is how short can be this pulse. And if you go to the Fourier Fourier transform, the shorter pulse, the broader spectrum, and then we can extend the scale. Let's say currently we can go up to 5 terahertz using antennas approach, and it's pretty good for spectroscopy. So, but what is important here is a so-called transient called around the fast Fourier transform, and here is a direct experiment. So in fact, terahertz spectrum, it's just mathematics, appears from mathematics, and this can be applied for analysis further. So usually how it works, and it's we need a femtosecond laser, we need very specific antenna, and let's say and semiconductor materials, which usually gallium arsenide, or initially it was silicon or sapphire substrate, given silicon with radiation damage. The radiation damage was needed to make a shorter time of life carriers. Otherwise, if you have long times, you can generate carriers. They are living and they are screening electric fields. It means electrons cannot be accelerated by the field applied on these antennas, and terahertz emission just is strongly reduced. So in fact, if we have certain kind of system, it works, and we have terahertz pulses. So in fact, choice of the material depends on the wide gap. Usually it's gallium arsenide. Depending on the laser system what you're applying here, it's if you have a, let's say, coherent or spectrophysic lasers, which sometimes sapphire laser, it operates about 800 nanometers. So we have gallium arsenide stuff, which exactly fits to fit the band gap, and for that we need very short lifetimes. And then if we look at the more details, here is antennas, here is the focus of the beam, and the dimensions are not critical for any unconventional, I would say, lithography. It's microns. You can use it nearly nearly in biggest majority of labs in the world in the processing, we do not need electron lithography. But the main trick here is the current which flowing through the device is picoamps. It's very, very low. It means we need a preamplifiers aiming to record the system. So what we have results of the specific collections of components. We have so-called transient in experiment and very nice spectrum, which is Fourier transform of the transients, which in fact is Terahertz domain spectroscopy. So if we go further, examples how we can use it and for what we can use it. First experiments, it was a big acceleration on that, how we can do. Professor X and Zhang group recorded a number of images in addition to Bell Labs' first report on semiconductor chips. It's a leaf, a fresh leaf, and 2 days old leaf, indicating the terahertz exactly feels that content of water. And so they recorded meat because idea was to apply imaging to estimate how old is the food, for instance, because it's mainly dependent on the content of the water. And it looks promising, but still hard to do it. Then it was big and still is big topic on application of terahertz for medical stuff. And the photos is in it's skin cancer detections. It's you see here is skin on the surface and go deeper in the skin. So in fact, since the water content is changing in the skin, you can see the change from the water contents, which can be indirect in illustration of cancer evolution in the tissue. And of course, security, airports and dielectric explosives can be one of those topics to use for terahertz, because it allows to see not metallic stuff which can be hidden in the pocket, but also dielectric stuff which can be dangerous also for other people. So in that non-contacting identification of materials also is big advantage for terahertz. We go further a little bit on that topic as well. So non-destructive testing, medical imaging, and security check is a main leading topics. So in fact, it is a two approach. First is to see something which is hidden in the pocket. Another is to identify. It's two different things. So that is why it's so-called terahertz spectroscopic imaging. Usually, spectroscopy, we see people can say that okay, it's good stuff, and you should measure spectrum because every material has a signatures, specific signatures on suitable for particular for this material. But in fact, if we have some stuff in the pockets, it's difficult to measure spectrum because of scattered light. So what people did, it's a Japanese group from Kodo Kawase, and Tonucci from Osaka University in Japan. They developed a tunable terahertz source based on lasers, still bulky system, but the principle is very nice. They have using two lasers and they're mixing them in lithium niobate crystal, which allows to generate tunable terahertz emission with a discrete frequency. And the advantage is to record the imaging in different frequencies, not spectrum, but just in different lines. It means so-called spectroscopic imaging. And here is codeine, cocaine, and sucrose different. And if we measure and different frequencies, you can see different shadows. And if we know in a priori that which kind of materials has specific absorption, we can say that this material can be dangerous or can be potentially identified if we know the spectrum initially. So in fact, we can identify materials without measuring directly spectra. So images and different distinct frequency. It is this principle of spectroscopic imaging. So what we're discussing here is bulky systems. In fact, there are meter long, 2 meters long, a lot of optical components, tiny alignment of optics, and so on, so on. We should go just. It's a very small system like mobile phone. Nobody cares how can I align my CCD camera, which decodes very nicely all pictures. So We should go in the similar way. And go, next topic is today towards compact terahertz imaging system. So what we can do first? So first principle, we're going back to this principle, classical picture of who and us, and what we can do in order to make the system more compact, or of course, from project side, more cheaper. So the most expensive thing here is femtosecond laser. So the first thing, what we can do is just eliminate it from here. So it means we can eliminate femtosecond later, but it's not enough. System will be not operating. So we need a replacement, and the possible replacement could be, let's say, for instance, quantum cascade laser. Okay, for the sample which sitting here, doesn't matter. Sample do not know from which kind of source terahertz appears, but in fact, for us, it will be good solution. And for instance, quantum cascade can be very rational options. It's very small device. It's very compatible. It's fixed. It operates in fixed frequency, but in initial phase, of course, is a big challenge is low temperatures, because usually quantum cascade lasers, it's usually in particular in terahertz regime, operates at low temperatures. So let's proceed. And now it was fantastic work made by Vienna group, headed by Karl Unterreiner, and also Jerome Fay's group and group from medicine people from Austria. 2 decades ago, they published interesting publication. It was first terahertz image using quantum cascade laser. What they use here is they used quantum cascade laser placed in cryo system here, and then they used parabolic mirrors and detectors. Also was we'll see it was also cool detector. So idea was to show in principle how is it possible to work or to apply terahertz quantum cascade lasers for imaging, and question is the quality. Recording, it was medical stuff. You see the red brain focal sections. They have 2 images, and they were recording them using quantum cascade laser operating at 3.4 terahertz. So what is here is good stuff. Quality is good, but here is cryo system. It means we need a helium system. It means big stuff on the optical table, and nothing to do with that. We have a liquid helium. Since we have liquid helium, we need liquid nitrogen. It's all the system. And also a detector here is also a helium-cooled bolometer. But in fact, doesn't matter if we could have good detector. We can just remove this and saying, okay, we can have a good recording here. So in fact, principle is shown. Quantum cascade can operate, but still a lot of issue, mainly related with a low temperature operation of devices and relevant setup arrangements. So it's good stuff. So okay, and the next step may be, okay, let's try to play with terahertz first. Okay, quantum cascade, let's leaving here, just replace terahertz detector. And another work which amazing, it's still more from my side, because usually, physicists have a feeling that if it's possible not to do something, it's also not to do something. So people from MIT and headed by Quinn Hu group, they used a microbolometer focal pre-arrayed together with quantum cascade laser. So what they set up was very similar to Vienna setup, but the main innovation here was microbolometer camera, and here is a parameter from them. So vanadium oxide based, it's commercially available camera. If you look at numbers here, it's infrared, purely infrared camera. It means they have a protection layer on the top, and they were able to remove it to increase absorption, because bolometers, it works, just doesn't matter which kind of sources they used, but since they feel the heat. So idea was, since here is atmospheric window, it's a lot of heat inside, but the idea was just to apply it for terahertz and to see how it works. It's commercial camera. It's real-time commercial camera. And idea was to see is it possible to play such a game when quantum cascade laser is still cooled, but here we have a room temperature operation of commercial available camera, infrared camera, but it uses for very specific range for 3.4 terahertz. So quantum cascade operates in very powerful regime, 50 milliwatts. 50 milliwatts, it's big numbers in terahertz. Still C33K, it's not an issue, but 50 milliwatts is a big numbers in terahertz powers. So what they did is first they recorded, they wrote with a pencil, MAT. A pencil is metallic stuff, mainly semi-metallic stuff. I would say this conductivity is good. It means I have good reflections and good absorption here. So transmission, no transmission, and good reflection here. And here's the fingerprint was colored with a graphite. But the most interesting stuff, they made a camera and ran it in the real time. And in fact, what we have, it's recording, a real-time recording of terahertz imaging. You see, electronics laboratory, MIT do. It means they were able to see written words inside the envelope. So it was real-time imaging, still really old, still impressive, but the conditions to realize it, we needed good powers. I mean, 50 milliwatts of quantum cascade laser or other kind of emitter in order to record this. So it was good result. It means we can go to real time and systems. So if we try to summarize of introduction part, what you can say is that in fact it's very convenient and non-destructive tool for various areas, but it's good. Room temperature operation can be somehow realized, but still systems are very expensive. And of course, for in particular, if we go for delicate devices, we need still cryogenic cooling. While in real operation conditions, nobody wants to have like any type of cooling, excluding any type of helium systems and even liquid nitrogen systems. It means, and another stuff is optics. I mean, all setups usually contains parabolic mirrors, which are not so big, but relatively bulky. But big, it means 2 inches somewhere else in this way, but still delicate stuff. In bulky stuff, it means precise alignment is everyday routine for to realize terahertz imaging. So if we go further, I mean, principles, and principles like Austin switch, it's which is used for nearly all, or at least majority of optoelectronic systems. And another approach can be done, let's say, optically pumped laser, which employs grating, tuning, and CO2 laser, and have, for instance, methanol gas in a specific kind of cavity. And what they can do, if try to compare these big approaches, devices are still bulky, but the scale can reach 7 terahertz. It meant, in fact, for laboratory conditions, we have very powerful and convenient tools to do that. And if we go in the parameter scale, I mean, milliwatts, we can reach in this system, we can reach 150 milliwatts, while for optoelectronic systems, microwatts is a big numbers. But in fact, we have coherent detections in contrast to the optically pumped lasers, which have like power detections and not always need to have a coherent detection here. So and if I try to illustrate by pictures here how it looks like, spectrophysics laser, which we have in our labs, is here, and our laser, let's say in Vilnius lab, have 2 meters long. And here is Terahertz company which tried to replace it with fiber lasers. It becomes small, and some devices for terahertz fuel becomes placeable on a hand. It means it's good progress in making system more friendly and more compact, and of course more effective. So now we're going to the solid state perspectives. And if we go back to my previous slide, the first first slide of the talk, and once again to see that terahertz are some specific kind of bridge between electronics and photonics. Today we'll talk about electronic sources, quantum cascade lasers, plasma devices or CMOS-based oscillators, plasma waves detectors as CMOS emitters, and something like that, and also Schottky's bow ties there as well, and bolometers, and to see how it's all of them, in fact, compact solutions. An idea is how we can combine terahertz system, because we need more power in sources, high sensitivity in centers, room temperature operation, as well, keeping in mind that all the system should be compact, and of course, if possible, to realize it without optical alignment would be absolutely fine. So in fact, no much freedom in devices, no much freedom in designs, but several approaches which I see as rational solutions to go further in development of compact and effective systems. So, and connections, finally, all those stuff is not enough. We need a very specific optical approach. Flat or diffractive optics is already previous, like was indicated previous lecture given by Professor Agnieszka Simeon. So let's go further. Emitters, main device and very popular device is to use electronic emitters. It means multipliers. You know, if you look at very primitive scheme, I mean, in fact, it operates that I can double frequency. If I try to find the regime somewhere here, I can have an oscillator circuit in a specific place of the circuit. I can double frequency. It means if I have 1 omega, output can be 2 omega. When we have megahertz, it's not an issue. I mean, principles is simple. We need non-linear element here. It can multiply, so-called flywheel effect, and we can have something like that. We need a flywheel effect. It means I'm trying to go squared, like cosine function goes squared. I have the second harmonic as a result of this square approach. So it's good. But when we go to higher frequencies, I mean, we have a so unpleasant stuff, it's so-called RC limitation. It means my device usually have a resistance and capacitance. It means that it will be very small since RC began to limit this operation. And in fact, if we look at this, how it looks like, this modern frequency multipliers, for instance, developed by Chalmers University in Sweden, they have very specific form. They have like a bridge. There is nothing below, because epsilon, which is a dielectrical permittivity of the materials, sometimes are removed just to try to reduce capacitance of the structure. Usually gallium arsenide, the dielectrical permittivity reaches 12. It means if I remove gallium arsenide from the game, I can win 10 times higher frequencies. It's big numbers and needs to be done. And so it's one of the technological ways to do that. And here is some integration of this device in the waveguide. So what we have here is quasi-optical. We can play not only waveguide schemes, optical schemes, and anyway, but stuff is delicate. We need a very precise game regarding electrical parameters, in particular resistance and capacitance. So another interesting approach, which mainly more dominating now, it's Charlottesville, Virginia Diets team, and they are doing like very popular commercial available system, like pumping scheme, which goes from 12 gigahertz, can multiply by several times and reaching, let's say, 2 terahertz. And that is good. I mean, we have tunability. We need it for spectroscopic imaging, but still system is electronic and allows us to go very far, very high in frequencies, and to work and selected frequencies 1-to-1. If you look at the numbers here, is usually they double or sometimes triple. There is no double, and all the stuff in multipliers are usually double or triple, not other numbers, just because of efficiency. And if you look at the numbers here, it means power level and frequency level. We can reach 2.6 terahertz in emission, but the range is only 2.5 microwatts. It's a very not big numbers. For imaging, we need a specific kind of detections and or specific kind of recording stuff in order to record qualitative imaging. If we try to summarize this electronic devices, also old work published by GPL group, we have a very interesting pod here, which is around 600 gigahertz. We'll see here is main security system operates here. It means 1 milliwatt. It's very important stuff. And then with what we have records, I mean, numbers at 2.5 can reach only 10 microwatts. It's big numbers here, and also goes. It was about nearly 1 decade already. No big improvement in the scale. It means it seems that systems already reaches a physical limit, and there is no big freedom to increase the power. So that's the numbers. So we have good numbers here at low frequencies and relatively small numbers at 2.5 terahertz. So here is important 1 milliwatts we're using as a reference, and this is a specific kind of circle indicates security application numbers here. And 1 milliwatts, we will see later, will be very important. And here is security area. So that it was emission stuff in using electronic emitters. So nanostructures for quantum cascade lasers, materials engineering, it's very primitive. Design technological approach is known from 1972 when MB structures technology was developed, and idea is to use superlattice and quantum wells to design new devices. Quantum cascade lasers is a good example of that. You had already a lecture on that. So just to remind you that in comparison to conventional semiconductor lasers, you need an electron-hole combination and to have photon emission. In quantum cascade laser, electron runs just via ladder down. It means they're losing energy, and every step it means emission of 1 photon. It means 1 electron can emit many photons, as many as you have cascades, how many cascades we have in the structure. So for that, 1 electron emits 1 photon. For that, electron can emit, let's say, 100 photons in the structure. And so here Bell Labs in discovery and invention, illustrations how quantum cascade laser can operate. And the first one was just developed in 1994 by Jerome Feist and Federico Capasso. It was indium gallium arsenide structure operated for infrared. And then, but for terahertz, it was a big issue, and it was developed much later, nearly 8 years later. We're using gallium arsenide structure, and operation was reached at 4.4 terahertz at 4K. So Alessandro Tedeschi and his team, together with people from Leeds, and they developed this. And the idea was to employ a specific design which allows to use electron-electron scattering for the population. So in fact, there is a very nice picture saying that when you have injection level, we have active level, and emission come from this side. You see this mini band engineering. We'll go for more the details here. We have mini band engineering, and we have something shaped mini band. It means electron has no freedom to go somewhere else except the point that we want, and have as emission to emit the light. So here's metal layer, metal contacts, and something like that. And the illustration of this is a sharp emission and this transition to the coherent emission of lasing at low temperatures. So what invention of terahertz quantum cascade laser, but still temperature was pretty low. From point of design, what is important for terahertz imaging, that terahertz lasers emits from the side. It means if we attach contact from here and from the top, emission goes from the side. Here is I took this from the classical work from Jerome Feist group, published many years ago. But if you look at the operation in particular, it's important for us. for imaging. Frequency scale is tunable for 1.9 up to 5.4 terahertz. Temperature range reaches only 250K. It's good. Maximum power, by the way, it's reached by Leeds Group. I would say it's world record. At 10K, they reach 2.4 watts, and at 2.8 terahertz. So this is an issue for terahertz imaging applications, and this is taken from the recent work 4 years ago, MIT, and they published this very nice picture here, but you see the power at 250K is still very weak. 250K is important because you can get rid of nitrogenic cooling because this temperature can be reached by applying, for instance, Peltier cooling, 2 Peltier cooling elements. It means no cryostat in the lab, no liquid nitrogen, no liquid helium, only Peltier cooling, which electrically driving. So that was big advantage of this approach. So in order to go to room temperatures, people played so-called intra-cavity mixing, and it is important stuff, mainly developed by the Zegi Group in America, in Chicago. And what they're doing here is making 2 lasers in this one, and they have interaction between artificially designed quantum wells, which distance in the levels was selected so that 2 infrared lasers exactly mixed in that, artificially in also called Chi2 in this structure. And so we have an intracavity mixing, 2 lasers in 1 laser, and it allows to emit terahertz. So it's room temperature. It's important stuff. Room temperature 4 terahertz, single mode operation, 8.5 microwatts, and it's room temperature. So it's everything in one, or everything inside. Is this current? Currents numbers are a little bit big, but still big promising, and we can go to optimization lasers. You see that 10 years ago, they have a 215 microwatts in this area. And then they published another work reaching, reaching 2.6 terahertz, and tunability and 1.0 milliwatt. So big advantage. It means we have options for terahertz spectroscopic imaging. It's not very big, not very wide, but still possible. And that is good way to go. No, it's in quantum cascade laser, and unusually in contrast to electrical devices, the limit or world records is a highest, for instance, in electronic multipliers. The more power and higher frequencies is some kind of milestone. Here's the opposite. To go to lower frequencies is a big issue, because in case you use to go to lower frequencies and the mode confinement, we use plasmonic waveguides, and absorption goes squared with a concentration. So lambda squared with a concentration. It means lower frequencies are strongly absorbed. We have big losses in the system. We cannot go very far, very nicely in the red wing of the emission. So resonant tunneling donuts, look at the papers with absolutely elegant device, and I took one of those important papers in the field, and they have very nice operation here. And the main idea is to go to this so-called negative differential conductivity regime. It means with the increase of voltage, the current decreases. It means if I calculate the power becomes negative. In physical terms, it means generation. So it works nicely, and this structure looks very sophisticated. I mean, it's good material engineering stuff, very elegant design. It's art of engineering. I think it's beautiful example. And here is the photos, how sharp this etching and how we can play with this structure. So from material point of view, it's not so complicated, but this part is some kind of highest engineering and art of engineering in electronics. So frequency world records now, it belongs to this Japanese group group. It's up to now, it's nearly 2 terahertz. And if we go to the large scale arrays and how much we can go, we can reach, let's say 1 terahertz, we can reach nearly 30 microwatts when we have element array of 89 elements. So that was good idea, very nice approach, very elegant device. However, it's art of technology. It's good for implementations, but it's very difficult to construct it. And plasmonic emitters, you know, it's alternative and an idea when we try to play a little bit with that. Instead of electron transport, we can use acoustic wave in two-dimensional channel. It means acoustic equivalent of acoustic wave in two-dimensional channel is just plasma wave. It can go faster than electron. Like, you know, if you are swimming, you are knocking with the stones in the water. So sound wave probably is pretty good in the water, but water itself doesn't move exactly as acoustic wave. So we can win 1 order of magnitude because sound wave is higher in 1 order of magnitude as electron. So, and the famous paper by Michael Shura and Michel Diakonov published 1993, and the formulas here looks very nicely. So if you look pretty well in this deeper, there is no, I mean, what is important here is dependence on N, concentration, and the sound speed can be changed by concentration. The concentration can be tuned by gate voltage. If we apply to tune the structure to the instability regime, we have very good emission, and the formula contains no any temperature. So it means it could be applied for low temperatures as well at room temperature, which is important for terahertz imaging. And then if you go to the plasmonic emitters, you see it was different approaches delivered by Montpellier group, and they observed this Diakonov showed instabilities and emission exactly related to this physics. But if you look at the emission, here's arbitrary units, how big is the power, which is a crucial parameter for imaging. And just I would like to mention also very nice cooperation of Vilnius and Warsaw group. It's old paper, but it was very nicely designed, and they give the numbers. The numbers are 100 of nanowatts. It's okay. In principle, it's compact solution, but still its powers are too low in comparison to imaging requirements, and maybe 110 case, still good for physics, very good for experiment in lab, but still far away from a real implementation. So what we could go further, it's CMOS emitters, and look at a group from Wuppertal, headed by Ulrich Pfeiffer, and they published that in fact what we could do with CMOS devices, we can make oscillators using CMOS approach, and using arrays we can reach nearly 1 terahertz with very good numbers, reaching 10, let's say slightly below 1 milliwatt, but we can go in 100 of milliwatt scale. And if we try to go to the structures for the heterodynamic and homodynamic imaging, and we can construct this very specific and very small in dimensions device, because CMOS, let's say silicon germanium source and silicon germanium detectors, you see the scale is very small. In fact, we have 40 centimeters. It's not meters, only centimeter scale, and lenses are still relatively massive, but still system becomes very effective, very compact, and contains minimal alignment. And they recorded very nice just demonstration of imaging with knife hidden in the specific kind of container. So let's summarize about emitters now. So plasma, you know, we are using this as the same way of electronic stuff. Here is plasma is sitting here, and maximum we can reach integrated of all emission, we can reach maximum 1 microwatt. Quantum cascade lasers are very far in the blue side, and still what we can reach only 2.4 terahertz. Sometimes and minimal is 1.9, but still at low temperatures. So it's a good point. We can go up in a powers, but still not enough for imaging, because it's pretty high frequencies in order to go with a good way. So resonant tunneling diodes can be good options. It covers a big range, and I plotted up to 1 terahertz, indicating that this can work about 40 microwatts here. They can go even further, reaching the world record, but emission powers are still low. And let's say silicon germanium oscillators can go up to 1 terahertz, and still keeping more or less good rational numbers for imaging. That may be one of the promising ground to go to proceed. In particular, if I plot once again security area, which is around here, it's very good indication for that. And here as illustration, here's I like Japan, and like Tokyo the post office. They implemented a security system here, and so what they have many envelopes running per day. And so if I put sucrose in the envelope and run to the system, and try to make spectroscopic imaging, you see very different kind of picture depending on the grain size, and the frequency you see it's nearly 600 gigahertz. Question is, why not lower? Because it will be cheaper. So grains are in the range of the wavelengths of half a millimeter. It means close to 600 giga. If we go lower frequencies, we have a cheaper system, but the accuracy is lost. If you go higher frequencies, we can better quality, but system becomes very complicated, expensive, and relatively hard to record because powers goes down. So in fact, some 0.6 and around 0.6 terahertz is a good rational option for security systems. That is why all people are looking around this and going to 1 milliwatt, which is an absolutely rational number for emission and to implement the system. So it's our photo of our lab, and here we have a VDI system which also sits in this lovely place of terahertz range. So requirements for sensing: room temperature, broadband sensitivity, and low NEP, low noise equivalent power. Requirements for optics: compact and minimum alignment. If you see here, you still have bulky system, which is not all the time is desirable. And of course, for emitters, room temperature, no question, power, tunability, and suitable mode. We'll see that mode can be aligned or changed depending on the aim of the setups. Let's go to solid state centers now. So I have just briefly and say words, just nice pictures, courtesy from Terahertz Technologies, company from Lithuania. You see is silicon lens coupled FET device for room temperature operation, and our cooperation with faculty of electrical engineering at Ljubljana University, and bolometric camera, which nearly is commercially available, and they operating at room temperature. They are very different devices, but still very good for depending on the range of application and the conditions of application. So nanometric transistors, once again, pioneering work by Wojtek Knapp in America, elegant experiment using Fujitsu transistors. We have 9040 nanometer scales. Wojtek and his co-workers observed very nice peak here, and he was big, and he was peak was in millivolts range. It's huge numbers. What is important is 600 gigahertz, while limitation was about 20 gigahertz, if I recall correctly. So in fact, this origin of peak of this kink and small peak was identified as a plasma wave manifestation in the channel. And that it was breakthrough allowed have to go big through in development of compact terahertz sensing. And this is famous formula developed by Diakonov and Schur, saying that in fact I have a good designs. I can change the wavelengths, I can change the mass, which is material parameter, and can have very elegant approach in detection. So that's important stuff. And let's say if we go to indium gallium arsenide stuff, which have lower mass than gallium arsenide, I can go to not only 600 giga, I can reach 3.1 terahertz in detection, which also extends facilities of compact imaging system. So, and one seminal work I would like to underline, CMOS works and seminal work of Wojtek Knapp group. Again, what they published, they implemented this silicon device in in an imaging system, which was antennas. They recorded needle in a chocolate, but it's not the best achievement. What they observed is noise equivalent power in silicon devices was in the range of 10 picowatts per square per hertz. So it was so big numbers, it's so impressive numbers, and was the main achievement. It was its room temperature. When we isolate bolometers have nearly the same numbers in liquid helium. That was breakthrough and seminal work saying that silicon is a material we should go, and silicon devices and CMOS detectors can be the breakthrough for imaging, in particular in compact size, effective wave, and in sensitivity. So that they made the recording, broadband antenna. It's good design solution for spectroscopy, and the most impressive number, which serves as a reference for many years already, it's NEP numbers in silicon. So later on, I mean, Alvydas Lisauskas and Frankfurt Group they made excellent, also seminal work, which is different from the extended approach in a comparison to Diakonov Schuh, taking into account as circuitry components, external capacitance, external resistances, and something like that. They developed nice array and recorded signals which reached 60 kilowatts per volt. It was 60 kilovolts per watt. It means huge numbers. But if you look at NEP, still 300 picowatts, it's higher than Wojtek Knapp group announced, but they found rational shoes. It was an array, and the brilliant recording of images in this paper. So it was shown that in fact we can go not only the single pixel, we can go with arrays, which allows us to record that also in real time. So if now and how far we can go with frequencies, our common work as well. So Vilnius and Frankfurt Group developed just array, which is colored array for terahertz, and each piece of this records different color. It means we can go to spectroscopic imaging. A unique experiment done in Dresden, in Frankfurt and Vilnius. So we see this curve, but the most important achievements, not only that we can go to 9 terahertz, we can make terahertz spectroscopic imaging everywhere and record this in a very compact way. It means we can apply not fundamental harmonic, but also third and fifth harmonic, and to see how it looks like imaging in this very broadband scale. So our common work, Frankfurt and Vilnius groups, just published a decade. What we did is development of good detectors, Terahertz with 30 nanometers technology, and ideas. What you see here is just simulators of explosive materials. We just used high density plant powder and compressed with tartaric acid and sucrose with different concentration. Initially, we measured spectrum using Fourier spectrum, and then we record it. We're trying to make photos of this and different frequencies, and this result is shown here. You see, so it is tartaric acid, sucrose, and a reference. What we have is for comparison here, and we have a recording at 0.7 terahertz and 2.5 terahertz. You see shadows are different. Still, here is a reference, still remain here. And if we try to go to reflection, in reflection mode becomes a little complicated. But if we use this colored photos in terahertz using CMOS technology, you see its extended scale. We can go up to 4.5 to 5 terahertz. A reference is visible, and shadow color is changing. And if you try to apply principal component analysis, we can see which kind of materials we have in every piece of this palette. So we have beautiful colored photos in invisible light in Terahertz recorded by CMOS technology of 90 nanometers node. It's pretty old stuff. By the way, mobile phones, using like 3 nanometers. So in fact, we have very old technology, which still allows us to go very high frequencies with a certain kind of designs. And finally, about diodes, we have bow tie diodes with broadband. It's development of Vilnius group, and the specific feature of the operation is just broadband operation. So we can go up to 2.5 terahertz at room temperature. The device can be placed directly on a silicon lens, and it can go and to see voltage which arise in a passive mode. There is no BS voltage depending on the incident light. So what we have is broad operation. However, is this numbers, if we compare with CMOS devices, are still not so good. So we need to do something different. And what we did is a coherent mode. We tried to make antenna bow tie arrays, and the device was coupled with additional antennas using indium gallium arsenide material and a relatively simple technology with using optical lithography and wet etching. So here is a photo of arrays. Only 8 devices were using in the line, and the total array is given here. And we use a heterodyne approach. It means we use 2 electronic sources which produces frequency around 0.6, the same reference for securities. And also, since we are using heterodyne, we used phase locking loop for here. So to record the frequencies and to see how parameters and images look like. So recording is something like that. We have NEP, which is 230 femtowatts, and we have records of Madsen hidden in an envelope, and also classical picture of leaf. It's freshly pressed, and then we record direct scheme, heterodyne scheme, and here is phase image, which allows to see optical light of the system because of weak absorption, the phase is still shifted, and it allows to see good picture. Here's for comparison classical work of XC Zhang group. So just we repeated it in a slightly different manner, and we're happy to that. Later we recorded phased image of former Lithuanian money, liters, and here is a coin, was our heraldic symbol, and which has appeared in a cover letter, cover of applied physics letter first. So continuous wave spectroscopic imaging bow ties, it's also the same. Samples were exactly the same, and procedure was exactly the same, and we did it exactly the same. So it works very nicely, and in fact, doesn't matter which kind of detectors we used. In principle, spectroscopic imaging has an option to use different kind of detectors to record good images and to define the composition and of the material, which can be in postal package or somewhere else. So bolometers. So, just why these devices are so good in comparison to let's say, bolometers. In the labs, it's a tradition to use bolometers. For instance, our lovely company for FTMC is bolometers. It's really big devices, and how big they are, here is a photo, which are close to the Fourier spectrometer. So it's a relatively big device, but we need liquid helium and liquid nitrogen to operate. And the parameters, you see sensitivity reaches about 3.5 kilovolts per watt, free ranges about 3 terahertz, and here you see this picowatt scale of NEP, which is, if you recall the previous slide, it's Wojtek group recorded the same number nearly at room temperature. So big advantage of silicon, and that is why I showed the slide showing how big is big advantage of CMOS technology in comparison to, say, conventional bolometers, which very often still used in labs. Our developments with Ljubljana groups, and what we did is a bolometric stuff. It's room temperature operations, titanium-based bolometer. emitters, and you say it looks like that. So we use a resonant cavity here, and what we achieved in this kind of devices is good operation. Operation is focused because we applied a resonance antenna. You see here is Gaussian mode, and this is good for imaging. And the imaging was recorded. The same samples were recorded using bolometers as well. So in fact, bolometers, compact bolometers, either bow ties or CMOS devices, also all Schottkys can be used for spectroscopic imaging and also discrimination of materials. So NEP numbers here in our bolometers reaches 20 picowatts, and in vacuum versions can reach up to 5 picowatts at room temperature. So it's good numbers. As illustration for mixing and another stuff, we recorded just distorted mode of optical photomixes. The mode is just initially was meant to be bad, just misaligned, to show this, and for the control it looks like this. So bolometers are very suitable and can be implemented in this stuff. And also photos at different colors here, and also bolometers picture made by one of our famous photo artist, Marius Jovic. Medical application. Bolometers application, what we observed here is Irmantas in our team here, together as well with Ljubljana group, medical stuff. We have a cancer-affected tissue placed in a paraffin, and what we assume here is like towards compound confocal microscopy. Is it runs each millimeter. The sample was 10 millimeter thick, so we can make each millimeter scan and to see all this structure inside the sample. So it's good application for imaging still, but sample is in vitro. It's paraffin environment, and but not in vivo because it's water. Because of water, I mean, would be a little big challenge. So now we have something like this one. So we should go to optics now. I mean, we have a compact emission options, we have compact detection options, but if we look to the optical side, we're not happy. We have still parabolic mirrors, still big, and idea is to replace them with the flat optics. So image, let's say, and the motivation, instead of that, we can have just very tiny silicon optics-based lenses or zone plates to use for chemical imaging. So let's go with let's say, for Fresnel zones. So in a previous lecture, you have heard about diffractive optics and the main formulas needed to calculate the structure. And in comparison to conventional optics and curved mirror, zone plates use diffraction instead of refraction or deflection. So our main approach will be usage of diffractive optics based on Fresnel zone plates. And what we did, we used laser ablation technology for this development. It was very, since we have many lasers, we try to avoid chemistry, and we use laser from XPLA at the moment. And what we did is this Fresnel zone plate. We're calling it multi-level phase zone plate, and we made specific study to understand what's the rational design for that. And what we understood is that, in fact, how many zones we need. Idea is only need a maximum 8 zones, because you go to the flat regime. In fact, is increase of number of zones increases time of production, increases the price of production, but still no big effect on effectivity. And this, it means 8 zones can be treated as a most rational option in designs. So large scale scope for 600 gig as well. So we're doing the same. 600 giga is our main frequency oriented to the security applications, and we try to go with comparison how good is our spatial resolution at 600 giga, and we see that still are in a good range, and resolution is in the range of waveframe. Sometimes it goes to 2 lambda, which is pretty enough in experiments going for security system. And another option is how go we can with light engineering. As a rule, in imaging, people are using Gaussian mode. We decided to learn a little bit on optics. First was going Fibonacci first, but the Bessel imaging was used just to have a good variety of options in using security check for postal envelopes, because Bessel beam is like a needle. It allows to have the same quality of a picture, even if as it's out of focus. It means main reference is 2 centimeters, because mainly it's conventional thickness of postal packages. So in fact, we started from Fibonacci and later go with Bessel, and now journey for education and application. So Fibonacci sequence is known, and in optics, you know, it's like Fibonacci sequence. Each number is the sum of 2 preceding numbers. So in optics, we have something like that. It means we have a radial, not simultaneously distanced optical stuff, which is so-called Fibonacci lens. And the main this particular feature is 2 points. It means it's bifocal operation, and this ratio between and distance between them is close to the golden ratio. We have some link with art. It means optics and art is pretty close to each other. So we try to follow this, and what we made initially, we designed simple our Fresnel zone plate, and then we designed Fibonacci plate, and we have 2 focuses here. In fact, we have a 2 bifocal operation. To illustrate it, we measured the distribution of intensity along the optical axis, and we observed two nicely expressed focused in the focus plane and the second focal plane, and we recorded this distribution intensity along this, and then we detuned that. We went away from the resonant frequency. Design was made 0.6, and we recorded 0.3. What we see here is it exactly fits that we expect here, and if we go to 0.3, we see that the second focus is just strongly diminished because it's out of resonance and out of any rational design for that. And so it's, since we have bifocal operation, we have a good and approximate golden ratio here. Let's go to the imaging. Initially designed sample, which allows us, the thickness was between the thickness was 7 millimeters, about the distances between both foci, and these objects were glued in different sides of this package, and this allows to see them simultaneously in the single scan. So it was just game to show that we have good operation and bifocal operation in Terahertz imaging, and Fibonacci imaging is possible and has this own area of application. So, but in fact, that is not so practical, because what we just need to connect the beams, to connect the focus, to have a needle here, and to have a so-called Bessel beam, and to have good operation in imaging. So Bessel beam is usually made by Exicon, and our Bessel zone plate was specific designs. They have a nicely, it was diameter of 20 millimeters. And here is a photo how we did it. It's only 4 zones we used for that, and the diameter of 20 millimeters to have a minimal optical losses. An idea also to see how the profile looks like, and it was precisely made. And we claim that laser ablation technology is good tool to do optical stuff using silicon for terahertz optics. So initially, modeling allows to see needle express shape, and here we have simulated Bessel, and we have experiments here as well. So we have good operation, which suits well could be suitable for imaging. And what we have here is removing all possible lenses from the setup. We're using 2 Bessel lenses and no parabolic mirrors. We have needle in the imaging, and then we try to go to see how the image can look like. And here is also our test, how good is our spatial resolution, and how we can how quality and in which quality we could expect in terahertz imaging. Initially, we observed this, and we see this comparison. We see it in the range. We are still close to a range of lambda. Here it's close to the lambda, but if we apply it to mathematical procedures, the convolution, we can go slightly below the frequency, below the lambda resolution, and for that experiment we used also artificial objects, which is just three-dimensional printing of plastic stuff, which allows to see how it looks like. So it's 4 different pieces which allows to increase the thickness of the object, and we see that in fact bezel images, it's good for thick objects in principle, can be extended and used nicely in postal office experiments. So good way to go, and what is important here is absence of any type of mirrors. And now idea is once again, more step further in learning optics, and one of these possible approaches could be IRI beams. So it means, we know how to make a needle, we know how to make 2 focals. The question is the possibility over the corner? I mean, IRI beam is just very specific way of light, which if it's curved. IRI beam is non-diffractive, self-bending, self-healing properties. In fact, IRI beam is described by very complicated formula, and it's not so elegant, but the results, well, we see it looks not so bad. So in fact, the idea is to make the curvature and to apply beam, and we had 2 aims. First is to learn optics, and then to apply it for terahertz imaging. So there are many different classes of accelerating beams, but we'll go to only for this way. So let's, until this movie runs, idea is how evolution looks like. It's modeling of IRI beam. We'll try to use it as example of structured light. It means electromagnetic wave. A structured light is electromagnetic wave with spatially inhomogeneous in amplitude, phase, and polarization. You see how it looks like? Our idea is to produce it in terahertz and to see how it can be useful for imaging. Let's go. So our design is simple. First we go zone plate, then we're using IRI plate, which is for zone plate we're using squared. I mean, this formula looks like this. Why is this one? And for IRI plate, it's a so-called cubic profile. And for comparison, we use bezel, all known bezel, hexagon, and fabrication. We changed our laser. We refused to go with picosecond. We went with a Pharos laser, with femtosecond laser, which found it better. And also our theory was just no analytical approach, Zomer-Rehave diffraction integral to calculate and to model all the stuff. So structured light and our terahertz beam, our paper published 2 years ago, we see theory and experiment. You see very nice pronounced structural light and experiment. We're using IRI zone planes and the zone plane, IRI plate and zone plane to collect the light. And you see this similar structure, which is pretty close to the model. And if you go deeper here, so theory experiments produce pretty well. So, but if we look at experimental curve, we need to enlarge it. You see this curvature, signatures of curvature, and there's a straight line here. So if we go this way, we see more pronounced, and also another parts are visible, a reciprocal, so-called reciprocal trajectories of IRI beam, which also inherent feature of such kind of structure. So we have IRI beam using no mirrors. We have only silicon optics inside. So let's go further. Imaging with zone plate. It's just show how it works and how the resolution can be seen. And then what we'll see is how we can select the optics and what the kind, what the quality of images can be done. And the main illustration, what we used is just try to cover biggest piece of the beam, putting metallic plate. So 10% coverage, 30% coverage, 50% coverage, and 60% coverage. IRI beam, IRI, the zone plate, and bezel beam. Here is resolution and contrast. Here is, you see, here is it's good. We have resolutions in a simple IRI beam in the range of 2 lambda. If we try to use zone plate, we can go even better. And if we go in this bezel beam, trying to cover this, is this bezel still visible? And if you see 50% is coverage, we still can see the pictures. So in fact, this IRI beam has as good options. No big change, no essential change, I would say, in resolution because of self-healing properties. In fact, it's good away. It can be useful for imaging from that point of view. So what we did, which kind of objects we can use, because it's not security or simulators of explosive materials are already done. What we use graphene for that. We made a special kind of graphene, 5 graphene layers on silicon, pure silicon, 1, 2, 3, 4, 5 graphene layers, and to see how it works in imaging. So initial test was IRI beam. First, we observed vibrations, identification of materials. That's okay. Photons. I mean, this spectra is conventional for graphene structures. What we observed here is we plot this to see what's the difference because of strain and because of inhomogeneities. Is it possible to see here? And we observed is zone plate comparison. First experiment with zone plate, which is this experiment, and IRI lens plus zone plate as a comparison for imaging. So if we look at this plot, I mean, is the change of the silicon graphite layers on silicon. Zone plate have monotonous development with the increase of thickness, while zone plate have very specific. So on silicon, we have certain kind of kink, which can be connected with the specifics of the specific layer because it has internal strain and depletion of carrier concentration. So Gaussian and tractor-restored light have different behavior in characterizing of materials. In order to understand, we just made a modeling graphene varying the refractive index because electromagnetic wave exactly sees only the change of dielectric function as polarized and p-polarized. If we look at this movie, it's very difficult to resolve differences. We see different evolution, but still they're not very clear. But if we plot a ratio of both that, we'll see that evolution of one polarization to the another one becomes strongly pronounced. Since we have structured light, it means our angle of incidence is relatively drastically different from Gaussian. It means we have a different behavior of the structures when structured light incidence in homogeneously or depleted or full of strain graphite layers on silicon. That is illustration that in fact structured light can be very delicate tool for non-destructive material characterization. What's important here? Since we start talking about very, very tiny optical things, our focus becomes very sharp. From the other side, our beams in optical scheme becomes far away, located far away from the optical axis. So in terms of optics, we can speak about non-paraxility of optical. Paraxial beams are pretty close to the optical beam, while non-paraxial are far away from optical axis. It means that if we try to make this stuff very sharp in terms of focus, our optics could be non-paraxial, not paraxial. What it means in terahertz, why it's important for terahertz. So non-paraxial, I mean, if we have paraxial gates, for instance, lambda, it's for Coherent laser, let's say infrared, we have the spot size of 200 micrometers. So all this time, the base is always bigger than the wavelengths. In terahertz, just opposite, 600 giga is about 0.5. Base can be in the millimeter scale, whereas the wavelengths in the similar range. So if we have paraxial case since theta with approximately theta, which is about 14 degrees, if the angles are higher, we try to deviate from paraxial optics and we go to the area to non-paraxial optics. It means our design principles can be strongly replaced. And we try to consider compact imaging system placed on a chip. Our way is not conventional optics. Our way will be non-paraxial optics with this tremendous integral, a Sommerfeld Rayleigh integral behind. And what we need to use is not simple optics formulas available from the textbook, but this numerical solution of this integral. So exact of complex solution, we can go with what can happen in imaging term. We are changing the language now. We are going to photography. If people are dealing with photography, the main characterization is modulation transfer function. It means in normal words that I should look how my intensity and the quality of image can be reproduced in image. So in fact, the term is not like a wavelengths, how many lines per millimeter we have in this term. So in fact, for Gaussian, we can have some like simple focus. If we go non-paraxial style, our picture becomes disturbed. It means our way, and in fact, what we have here is non-paraxiality. It means that my best resolution does not necessarily coincide with the maximum intensity. That is the main difference. It means that every step I should calculate precisely in order to know what the good place and optimal place to put my mirrors and collective or illumination optics in my setup. So in fact, what we have here is so-called depths of focus, which extend usually around this optical axis. But these areas, are totally different, and this resolution areas and incidentity areas requires topical study. We did, by the way, we did it in a recent publication of this year. So today, in addition, light engineering, is the last part of my lecture, is the light engineering. In particular, emphasis was collection and illumination and diffraction and collection of optics. And question is, what the design principles can be done and can be announced when we're trying to play with non-paraxial approach in Terahertz imaging. So as already mentioned, transfer function, it's known from photography, and we will look at it, and we will consider in terms of modulation transfer function. And this is our contrast to conventional photography. Depth of focus will be one of our parameters, and to see how it works in comparison to imaging stuff. So we'll see that in fact good quality of image can be obtained in certain area, but only in specific place with a resolution nearly reaching, let's say, 2 millimeters, 2 lines per millimeter can be reached only specific ways in very specific distance. So let's go further. Point of departure from optical side and from some imaging side. For single shot method, it means we have plane waves. It means we can conventional lens formula, which is known. So paraxial case, it means nothing specifics. We can find it in every textbook. We have operation of formula of lens formula with a certainly very nicely expressed focus. If we go non-paraxial case, our picture becomes disturbed. If we go single pixel method, which is very conventional for imaging, and people try not often use arrays, so our approach will be not plane wave, our single source. And if we have non-paraxial case, our formula becomes not valid. It means paraxial case, we have something like that. Non-paraxial case, we have sawtooth-like structure, which needs to be calculated initially in order to have good optical quality in Terahertz imaging. So classical lens formula is no longer valid, and we should go to the digital 12 of Rayleigh integral. The game is very similar. Zone plate and Fibonacci, we did the same as already talked about this. What we tried to understood, we tried to convert this imaging language to the language of modulation transfer function to see how a resolution goes and how it works. If we go deeper, and which is most important, Bessel zone plate and iris zone plate. If we look at these images here, when we are using a lens for Bessel and zone plate collection, we see absolutely non-suitable, for imaging stuff, which it means there is no rational place was to place a mirror and to find a good option for good resolution. And for zone plate, for instance, here, zone plate and Bessel, so illuminating optics is based on zone plate, collection optic is simply Bessel. We have totally opposite. We have very nicely pronounced depths of focus, and still we have a good resolution reaching 2 lines per millimeter. It means in the range 0.5, it means wavelength is 0.5, it means 2 millimeters per line, it means a wavelength. So in fact, we have a certain kind of places we can reach wavelength resolution in terms of imaging. So depth of focus is pretty big. If we plot it in modulation transfer function, we have very nice behavior as well, and we can compare how it works. Fibonacci's, Bessel, and iris zone plates. So if we go further, so you see this picture is not changing so much. So in fact, if we change iris zone plate and iris zone plate for emission and the second iris plate for collection, the picture is not uniform. Still, we have non-homogeneous distribution along the optical axis with strongly pronounced maxima with a good resolution reaching the wavelengths resolution. So in fact, it's a good one. So, in fact, what can be said is that design a non-paraxial system becomes complicated and hardly predictable by conventional logic. We need a code. We should calculate and then only place or collecting or illuminating optics in certain places and to try to record images, and then only then we could expect a rational approach to this and maybe good quality or good quality enough for imaging. Another idea is it possible to shift with the optimal place of the sample what we want to shift it? So in fact, what we have is a movement of distance are shift, but we were moving the sample here. So in fact, depending on the collection and emission illumination optics, pictures are totally different. Fibonacci and zone plate, and as you see, nothing happens. But we have zone plate and Bessel and Bessel beam and zone plate. You see very different. So Bessel beam is good for collecting optics, but for generation of structured light is better to use in this case. In this geometry, I would say it's better to use a zone plate approach. Iris beam is pretty good. Iris still has very specific areas with a very good depth of focus, but still keeping good resolution in also in collection scheme. So Iris approach seems more universal in comparison to others. So there's a specific points I indicated here. So if we try to go to various doublets, Iris, and Bessel, so it means that Bessel, it's absolutely not rational, good for maybe for modern art, but not so for implementation. Where Iris has very specific approach here, and also very good operation area and design for freedom, in particular in the terms of depth of focus. And Fibonacci probably is more for education than for real implementations. So in fact, if we go to structured light, it means that iris beam can be very good way to go. And we collect properly the collection scheme and illumination schemes, we can go and have very good compact imaging system. So depth of focus. So in fact, depth of focus, it means it is different from depth of field, because because we're trying to move zone plate object with respect to object. So in fact, in case of focus, in case of depth of focus, and depth of field, we talked on the object area. When we go to the depth of focus, we talked with the image area. So once again, what we have is Bessel zone plate seems to be good because we have freedom of 2 millimeters. Iris zone plates, some similar numbers. The rational place to along this axis is about 1.6 millimeters. While iris zone plate, iris have very strongly expressed the depths of field, depths of focus in very limited area. So in fact, there is better probably to go with very specific approach with a very specific aim for which aims the system can be designed and for which aim we can apply the system. And depending on that, we try to design materials, design optical components in order to have good approach for the optimal compact system. So in fact, this systems allows us to claim that this approach has some kind two volumes. The first volume is depth of field, which is mainly defined by the area, which is related with the object. And this one, which was depth of focus, are mainly related with area regarding image. So freedom is much allowed, but a rational composition is strongly restricted, and the main rules come from digital solutions from Rayleigh-Sommerfeld integral. So what we could say now about this kind of principles, what happens if we go to the light engineering in non-paraxial terahertz imaging? So first, non-paraxial regime seems to be good options because it allows to improve the contrast, resolution, and depth of field when structured light appears in imaging system. That is a good way. Another way is important that in fact is difference, which is sharp difference to conventional optics, that optimal modulation transfer conditions appears to be decoupled from the conditions of the best image. So it means that this is totally different from conventional photography. For each time we need specific kind of calculations and select specific place to put your illuminating or collecting optics in the imaging setup. So, and the way to do this is rational design rules only determined by numerical solution of Rayleigh-Sommerfeld diffraction integral. In normal experimental language, it means big friendship of theoretical people from optics sides and experimental people from laboratory side. I mean, the non-conventional terahertz imaging just an area and space to establish synergy of cooperations. Otherwise, result would be not as good as we could expect. And finally, it means every collection of these optical rules is unique for every aim. So it means that if we have a aim to design security system, what we should go with very specific rational design, asking people to calculate and then putting elements in a certain place of your setup. Then we could expect good result and qualitative imaging. So what we could expect tomorrow. So what we talked today, we have many options in emitters, and we had many options in detections. So there are many already works, what I already mentioned today. They were coupled, and if they can be paired in an experiment, it means electron devices, base sources can be recorded, emission can be recorded in viewing variety of the detectors and and devices. So we have different kind of sources, but we can also play a little mixture scheme. It means different kind of detectors and different kind of sources can be decoded or characterized in a different way. As one example, I would like to just to mention one work made by Frankfurt group together with Vilnius group. They used field effect transistor detectors, power monitor of Terahertz quantum cascade lasers, and the operation was 4.55 terahertz, and they use it for room temperature recording or using terahertz field effect transistors. Nice result, and which shows us how good is an options using CMOS devices and how promising can be quantum cascade lasers if we go to room temperature operation. What we expect more, in my opinion, we can expect some big breakthrough in indium phosphide related structures, in particular for making Terahertz emissions sources, because their frequency can reach 800 gigahertz and keep very useful for compact Terahertz imaging. We could expect also development of Terahertz integrated circuits, in particular gallium arsenide based, because it's optoelectronic materials, and it'll be a good platform to try to unite the optical properties and electronic properties in a single chip. And also, what is interesting, what could be expect in compact Terahertz imaging system? So, application on implementation of silicon germanium or BCMOS terahertz oscillators, which are recent work made by Warsaw and Vilnius group dedicated to interferometry using 130 nanometers BCMOS technology. They recorded nice images operating at 200 and 260 gigahertz, and here is samples are different kind of foils and allows you to see good contrast at good quality in very compact scheme. So that's what we'd expect in imaging. What we could expect in structured light, probably there is also imaging area. As far as I know, have only 2 or 3 works unknownly announced on application Terahertz communication, and one of the latest one is presented by Daniel Mitteln group. They illustrated curving Terahertz wireless data link around obstacles, and the range was 2 meters and 70 centimeters here, and they recorded very nice tracks showing that in fact Terahertz structured light can be an option for Terahertz communications, and here is good indication for that one. The illustration was provided by measuring communication stuff using linear phase zone plate and cubic phase plate, which is best. In fact, it's highly beam plate, and they indicated it in this so-called 6G area of frequency scale. It means slightly above 200 gigahertz. So further step, longer distances, nobody knows exactly how far we can go, but still more powers and more advanced evolutions in signal processing are needed for that. So optimal optic solutions, because we need a relatively big distance to manage the beam. It means that induces increase in the scale of optical elements. So my final slide is just to show you as outro or sham of Terahertz imaging. If you look at many years ago, let's say it's the first impressive image that I have seen. It was Montpellier and Frankfurt group recording of very nice cross placed in the paper envelope, which was using gallium arsenide, commercial aluminum gallium arsenide technology with a 250 nanometers gate. It's 2008. A later year, Vilnius group just published this insight how we can see content of medicine capsule and to see the level of medicine inside without not opening it. What was a bit recently finally, we showed that in fact terahertz structured light can be a good way to go in imaging and probably good way to go in communications. And we're happy to be in the front cover of Laser and Photonics Reviews, where our image shows terahertz sound distributing this airy curved, airy shaped beams over the world. And you see here is our different designs of wave plates producing different types of laser engineering beings. And finally, which seems to be very promising as well, is our nice work together with Professor Agnieszka Semyon group regarding color digital photography. We made it above 1 terahertz, and here is a reconstructed beam, reconstructed images of artificially made objects, allowing it to combine different colors, not in a conventional photography, but in digital holography, which allows us to go that probably it could be a way to go to also for materials inspections and probably non-destructive characterization of pieces of art. So that is charm of terahertz, that is charm of terahertz imaging, and I believe that this hot wave, which is still going in terahertz computing regarding manipulation, processing, and development of terahertz technology, will still keep a trend for evolution, will open new application area, and for us will be a good area to learn a little more and to see the beauty of physics. So thank you very much for your attention, and your questions are very, very welcome. Thank you.
I think this is the last lecture, so we need to give a few more minutes to our attendees to come up with some questions. Agnieszka, maybe you would like to comment a little bit on
I think we had a nice summing up of all lectures, because we went through different topics that we already part of them somehow discussed. But still, like Gintar, how do you think, in which way we will go in terahertz, let's say, field next years?
Well, I mean, what is interesting, I mean, it's so much done already, it's very, 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 very hot area still, but what I believe that the compact system, I mean, in particular, when you're going to very small, tiny system will be the way to go. This is one way. I mean, different topic is like CMOS oscillators or BCMOS technology. Probably it's in indium phosphide, because it allows to go to nearly up to 1 terahertz. We'll see how the powers. For optics, Aga, for us also it will be good because I mean, I still believe we're doing now with structured light as well. So with like vortexes in imaging, it allows to see different properties of materials, in particular when you have tiny structures like graphene, also maybe other two-dimensional materials like bismuth, for instance. We have a bismuth growth, so we're trying now to grow to see is it possible to apply structured light, because we have big angle of incidence which allows to see the phase shifts, and it means we can see this evolution. That may be one of the ways. Another is maybe it seems to be that this pairs of CMOS devices or BCMOS devices, which are very small, they can be used in real operational conditions. And no alignment you can place on a chip, everything that can be very, very convenient, because you can imagine femtosecond laser hardly impossible to see somewhere in the airport, because it's so big and so on. So we need a good guy who is served for this, because otherwise it's difficult. So we need a maybe very simple solution without not alignment, and also probably artificial intelligence introductions in the object recognitions. Several papers already appeared on that. So probably because object recognition, in particular spectral, I mean, if you measure spectrum, not spectrum, in fact, different colors, because spectrum is difficult to measure because it depends on your clothing. Shirts, jeans, and cotton or raincoat is totally different materials. It means different scattering light. It means very difficult to measure and identify. So error factor becomes hugely pronounced. So we should have to diminish this, and probably this multispectral imaging could be an option. In particular, I would say that holography, holography can be the way to go, because then it's sensitive to the size and maybe surface roughness, inhomogeneities in very tiny way, because absorption is minimal, but the phase shift is crucial. That can be an option. That I see that good cooperation link with Agnieszka, and going maybe compact optics directly on a chip. That can be one of the hottest topics, in my opinion. I have seen, and in conferences as well, it seems that people are considering this, because free space is one story, operation in optics directly on a chip is another story. Just very recent paper, by the way, you can look at how can you manage is very nice work by Jean de Corneau group from France. Just Nature this summer. It's very nicely how you can distribute light directly on a chip, but it's dedicated, for communications, for security. A slightly ambition as a story, but in fact, there's still a good area to go. That is my personal opinion. It's not. I'm not sure whether I'm not right, but it seems to me that it could be a good way to go.
Good direction.
Yeah.
So now all we can do is wait for the next Nobel Prize for on-chip terahertz. Okay, I think everyone feels like your lecture was extremely clear and well said. So with that, let's thank once again Gintaras for his brilliant lecture and the Q&A session. And so what this means is that the Candela Open Lecture Series on terahertz radiation has officially come to an end. But before we hang up, I'd like to thank all of our magnificent speakers for their insightful lectures. And I'd also like to emphasize that some of these lectures were given way outside of their comfortable local time zones, which makes us so much more grateful for their support and, well, the contribution to teaching optics and photonics on terahertz radiation to the next generations of Polish scientists. And next, I'd also like to thank the two chairs of this series, namely Agnieszka Siemion from the Faculty of Physics at the Warsaw University of Technology in Poland, and Łukasz Starczewski from the Faculty of Electronics, Photonics and Macrosystems, I think, yes, from Wrocław University of Science and Technology, also in Poland. I'd like to stress that without their support and wide network of collaborators, organizing this lecture series on this level would not be possible. And I also think it's worth noting that Agnieszka was actually present during every single lecture in the series, which is a first for us and something we appreciate really greatly. So thank you. And last but not least, I'd like to thank all of you for joining us for this series. At one point, we had almost 100 attendees, which we consider a major success. And to us, it's an indicator of sorts that such a lecture series on hot topics prepared in high quality and available for free are something that our community needs and appreciates. And with that, I'd like to invite you to the next lecture series that will start sometime in March 2025 on the topic of Bose-Einstein condensation in both atomic and solid-state systems. And the easiest way to get notified about that series and the next series that are coming next is to follow us on our social media at Candela Foundation. So with this lengthy ending, thank you all once again for coming and for listening to the lectures, and hopefully see you soon in March. Thank you very much.
Bye bye.
Bye bye.
Thank you.